So, welcome to chapter 35, which is all about the interference. So, in this chapter, we will explore one of the most important phenomena that proves light behaves like a wave, and which is all about the interference. So, just like sound waves or water waves, light waves can combine, sometimes adding together to become a brighter, sometimes canceling out to becoming all dark. So this explains many color effects we see every day, and it forms the basis for precision measurement tools used in science and engineering. So here is what we learn in this chapter. First is we'll look at how waves interact when they travel through space and overlap. Then we'll focus on the classic experiment, two-source interference, called the Young's double-slit experiment. So this is the experiment that first proved light is a wave. So we'll go beyond just finding where bright and dark spots are. We are also calculating how bright they are. This is about the intensity. So next, we'll study thin film interference, which is what makes soap bubbles and oil slicks colorful. So finally, we will see how scientists use interference patterns to measure the difference or distance as small as the diameter of an atom. So let's start with two familiar questions. First is, the soap bubbles are made of clear, colorless water and soap, yet when you look at them, you see a brilliant rainbow color. So where do these colors come from? Second, when you hold a DVD or CD up to light, it reflects light, shifting colors, even though the plastic itself is clear. So the answer is both interference. These effects cannot be explained by thinking of light as rays traveling in the straight lines. So we must treat light as a wave. So this chapter is all about what happens when light waves meet and combine. So before we talk about light, let's remember how waves are formed. Imagine dropping a stone into the water. It ripples spread in circles. So these are wave fronts. Light waves behave the same way, spreading out from a source. So the most important rule here is the superposition principle. So if two waves travel through the same point in the space at the same time, they don't crash into each other or bounce off. Instead, they simply add together if both waves are moving upward. So the total displacement is bigger. If one is up and the other is down, they cancel out. This adding and cancelling is exactly what causes the interference. Now look at two sources creating waves at the same time. In step with each other, we call these coherent sources. Where do we get these big waves? So wherever the peak from one source meets the peak from the other, here the path difference. So this difference is the distance each wave traveled is exactly one wavelength or two wavelengths or any whole number of wavelengths. So the waves arrive in phase, add together and make extra large waves. So this is a constructive interference. So where do we get calm water? Where a peak from one meets a throw from the other. So here is the path difference is 1/2 lambda, 1 and 1/2 lambda, and etc. So the waves arrive out of phase, subtract from each other, and cancel completely. So this is the destructive interference, where the light does exactly the same thing, constructive interference, bright light, while the destructive interference is equal to darkness. So this diagram puts it all together, so we can see here the path difference clearly. So the lower rate travels farther, where the difference is a whole number of wavelengths: bright fringe, half integer, and dark fringe. So this simple formula, so let us calculate wavelength if we know the geometry, or find distance if we know the wavelength. So in 1801, Thomas Young did exactly this experiment with a light. He shone light through two very narrow, closely spaced slits. So if light were made of particles, you would just see two bright lines on the screen behind. So instead, he saw a pattern of many bright and dark fringes, proof that light is a wave. So let's look at the geometry, where the light comes from the left, passes through slit 1 and the slit 2. So to reach a point on the screen, light from the lower slit has to travel a tiny bit farther than light from the upper slit. So the extra distance is the path difference. So here is from the angle. If the angle is small, we find this equation, where d is the distance between the two slits. So let's work together through this example 35.1. So we have a given slit separation, d is equal to 0.25 millimeter, or on the other, 0.25 times 10 to the negative 3 meter. So next is the distance to screen, r is equal to 1.2 meter. And lastly is distance from center to third bright fringe is equal to y sub 3 is equal to 9.0 millimeter is equal to 9.0 times 10 to the power of negative 3 meter. So we want lambda used, or the wavelength. So here is the equation. So y sub m is equal to r multiplied by m lambda over the d. So simply, we rearrange this equation. So it turns out lambda is equal to y sub m times d over the m times the radius. So just simply plug in the numbers here, and it results as 625 nanometer. So this is red-orange light. So this is exactly how we measure light wavelengths in some laboratory. So interference isn't just for light. It works for all waves, including the radio waves. Example here in 35.2, where two radio antennas act like two sources separated by d is equal to 400 meter, while the frequency is equal to 1500 kilohertz. So first is we find the wavelength. So here is the equation of the wavelength, which is represents the lambda is equal to c over the frequency. So just simply put together and it results 200 meter. So the maxima when d sine theta is equal to meter lambda, the sine theta is equal to m lambda over d is equal to m multiplied by 200 divide 400 is equal to meter over the 2. So this is the possible m values 0, 1, and 2. So since sine theta is less than 1, so here is the equation that can be formed. So these are the directions where the signal is strongest. So between them, the signal cancels out. This is how broadcast engineers designs antenna arrays to aim the signals in the specific directions. So far, we've said lately bright is equal to maximum, dark is equal to 0, but what about in between? How bright is it exactly? So we calculate intensity. So we represent each wave's electric field is a phasor. So phasor, it is a vector whose length is the amplitude and whose angle is the phase. So when two waves meet together, we add the phasor's tip to tail. So if each wave has an amplitude and the phase difference is, the resultant amplitude is found using the law of cosine. So this is how the formula or the equation are. So intensity of light is proportional to the square of the electric field amplitude. So if both waves have an intensity alone, maximum intensity when they add is equal to 4, 1 sub 1. So this is 4 times as bright as one source. So at any phase difference, this is the K formula. It tells us exactly how bright the light is at any point. So here is the equation. And now connect phase difference to position on the screen. So if the path difference is 1 full of wavelength or the lambda sub 1, the waves are shifted by exactly 1 full cycle, or the phase difference is equal to 2 pi radians. So here is the equation, and then simply plug this into our intensity formula. So here in the screen attached, so this is the complete mathematical description of two-slit pattern. So the graph shows exactly what you see, equally spaced bright fringes. So fading smoothly to 0 between them. So example 35.3 walks through a numerical calculation using this formula. Now we move from the two slits to thin film interference. So this is the physics behind the soap bubbles, oil slicks, and anti-glare glasses. So the idea is the same. Two waves, path difference, interference, but here the two waves come from the reflection. First is light reflects off the top surface of the film. Second is light also goes through the film, reflects off the bottom surface, and come back out. So these two reflected waves traveled different distance. That one went through the film and back. That extra distance create the path difference. So from figure 35.12 shows an air wedge, which two flat glasses plates touching at one edges, separated by a thin wedge of air at the other. So the light reflects off the bottom, the top plate, and top of the bottom plate, where the changing of thickness creates a parallel bright and dark fringes. Here is the crucial detail. So phase shifts upon reflection. So when light travels from a medium with lower refracted index and to one with a higher end, like water to water or air to glass, so the reflected wave flips upside down. That's a 180 degrees phase shift. So exactly the same as if it had traveled an extra half wavelength. So when it goes from higher to lower, like a glass to air, there is no flip or no shift. So this changes everything. In thin films, you must account for both. First is the path difference from traveling through the film twice, or it down and back up. Second is any phase shifts from reflections. For example, in an air wedge between glass, one reflection has a shift, the other doesn't. That's why the contact point is dark and the two waves are out of phase. So let's apply this step by step using strategy 35.1. First is identify the two reflected waves. Second, check for phase shifts. Third is calculate the path difference is equal to 2, or the thickness refractive index, because the light travels slower in the film, wavelength changes. Fourth is set conditions. So the bright is equal to total difference is integer of the wavelength, while the dark is for the total difference is equal to half integer only. So example in 35.4, where the air between the glass plates, we find how thickness relates to the fringe position. Example 35.5 is replace air with water, where n is equal to 1.33. The wavelength inside is shorter, so the fringes get closer together. And lastly is the example 35.6. This uses these principles to measure the very small thickness. A famous variation where is the Newton's ring. Place a flat glass plate and a convex lens together, so they touch at the center and the gap between them increases outward like a circle. So the air gap thickness is the same all around any given radius. So for the result, instead of the straight fringes, you get a perfect concentric rings. So the center is dark because of the phase shift rule we just discussed. So this pattern was studied by Newton. So though he couldn't explain it because he didn't believe light as a wave. So this is used industrially. So to check if a lens is perfectly shaped, you place it on the top of a master lens that is known to be perfect. So if your lens is exactly the right shape, the air gap is the same everywhere, which you can see one solid color. So if your lens is slightly wrong, the gap changes thickness in different places, and you see a rings or curves. So each ring represents exactly one wavelength difference in height. So you can measure errors smaller than 1/1,000,000th of a meter just by looking at the pattern. Finally, the most famous interference instrument, which is the Michelson interferometer. Here is how it works. First is a beam splitter divides light into two paths. Second is one beam goes to a fixed mirror, the other to a movable mirror. And third is both reflect back and recombine. And lastly is you can see an interference pattern. So if you move the movable mirror by exactly the lambda over 2, the path difference changes by a full wavelength, and the pattern shifts by one whole fringe. So because wavelengths are so small, like hundreds of nanometers, so this device let us measure distance with incredible precision, better than a billionth of a meter. So it was used to define the meter for many years, and it was the tool used in the Michelson-Morley experiment that paved the way for Einstein's relativity. So ever wonder why camera lenses or the eyeglasses have a purplish or greenish tint? So that's a non-reflective coating. So you put a very thin layer of a material like a magnesium fluoride on the top of a glass, then the light reflects off the top of the coating and off the coating glass boundary. So you choose the thickness, so the path difference is exactly lambda over 2, and you choose the refractive index so that the one reflection shifts and the other doesn't. So the result is the two reflected waves cancel completely destructive interference. There is almost no light reflects, almost all passes through. So this makes images brighter and reduces the glare, which is example here in 35.7 that calculates exactly what thickness is needed.